Welcome to one of our Space Science and Technology Portals lectures. The title of this lecture is An Introduction. In this lecture, we tackle the following topics. Topic number 1. What is orbital mechanics or astrodynamics? Topic number 2. How has the idea of a satellite been created? Topic number 3. What are Newton's laws of motion? Topic number 4. What are Keplers laws? Now we start with what is orbital mechanics or astrodynamics? Orbital mechanics or astrodynamics is the application of ballistics and celestial mechanics to the practical problems concerning the motion of rockets or other spacecraft. The motion of these objects is usually calculated by Newton's laws of motion and law of universal gravitation. Orbital mechanics is a core discipline within space mission design and control. Celestial mechanics treats more broadly the orbital dynamics of systems under the influence of gravity, including both spacecraft and natural astronomical bodies such as star systems, planets, moons, and comets. Orbital mechanics focuses on spacecraft trajectories, including orbital maneuvers, orbital plane changes, and interplanetary transfers. It is also used by mission planners to predict the results of propulsive maneuvers. General relativity is a more exact theory than Newton's laws for calculating orbits and is sometimes necessary for greater accuracy or in high gravity situations such as orbits near the Sun. Now we move to how has the idea of a satellite been created? To understand the theory of satellites, we first have to understand the following simplified example. Imagine that you are holding a thread with a heavy ball at its end, and you are rotating it strongly in one direction. What will you observe? You will observe that the ball keeps rotating with the thread stretched holding the ball, preventing it from being thrown away. The same theory can be applied to satellites, where a satellite represents the heavy ball, the Earth represents your hand, and finally the thread represents the balance between the Earth's gravitational force towards the Earth's center and the centrifugal force away from the center, as in the previous example. The rotation of a satellite in its orbit results from its force of inertia during in-orbit injection. This centrifugal force arises from the final launching phase of the rocket, where the satellite is positioned in its orbit. At this stage, the satellite is launched from the rocket with a specified angle of inclination and a highly accurate calculated force that gives it the ability to move in its orbit around Earth. It is theoretically assumed that a satellite continues to rotate forever due to the absence of resistance outside the atmosphere, where there is no friction between the satellite and anything else like air. Thus, applying Newton's law, for every action there is a reaction, equal in magnitude but opposite in direction. Now we move to what are Newton's laws of motion? Isaac Newton, 1642 to 1727, established the fundamentals of celestial mechanics based on the earlier work of Tycho and Kepler. Newton formulated the basic concepts of the laws of motion and law of gravitation around 1666, but it was not until 1687, at the urging of Edmund Halley, that the principle was published. The following 3 laws of motion given by Newton are considered the axioms of mechanics. First law: every body continues in its state of rest or of uniform motion in a straight line unless it is compelled to change that state by forces impressed upon it. This sounds trivial to us, but in the 17th century this was new. Second law. The change of motion is proportional to the motive force impressed and is made in the direction of the straight line in which that force is impressed. F vector equals dmv vector by dt. If a body's mass does not change, then this can be explained by the well-known equation F equals ma. If a body's mass does change, then this may be used to derive the ideal rocket equation. Third law. To every action there is always an equal opposing reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. Universal law of gravitation. The principle also includes the universal law of gravitation, which is usually stated as every particle attracts every other particle in the universe with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. We can express this law mathematically in vector notation as Fg vector equals minus gm earth m sat by r square dot r vector over r magnitude, where Fg vector is the force on the satellite of mass m sat due to the earth of mass m earth, and r vector is the vector from m earth to m sat. As a consequence of Newton's universal law of gravitation, Kepler's elliptical motion model is extended to any conic section. Now we move to, what are Kepler's laws? The track of an object through space is called an orbit. Kepler initially assumed that the orbits of planets were circles, but doing so did not allow him to find orbits that were consistent with Brahe's observation. Working with the data he obtained by observing Mars, he eventually discovered that the orbit of that planet had the shape of somewhat flattened circle or ellipse. Next to the circle, the ellipse is the simplest kind of a closed curve, belonging to a family of curves known as conic sections. He was able to find the first law. Kepler's first law, law of ellipses. The orbits of the planets are ellipses with the Sun at one focus. When applying this law on satellites, we can say that the orbits of satellites around the Earth are ellipses with the Earth at one focus. The same law applies to satellite rotation around Earth, where Earth is located at F, while F' is empty, where A, semi-major, B, semi-minor axis, E, eccentricity, theta, true anomaly. The position is defined by r and theta. R equals A times 1 minus E power 2 over 1 minus E cosine theta, for E is greater than or equals 0 and less than 1. Eccentricity describes the shape E equals the root of 1 minus B over A squared. Kepler's second law, law of equal areas. The line joining the planet to the center of the Sun sweeps out equal areas in equal times. We can deduce that a satellite moves fastest when it is closest to the Earth and slowest when it is farthest from the Earth, except for circular orbits where its distance from the Earth is fixed. Kepler's third law, law of harmonics. The squares of the periods of two planets' orbits are proportional to each other as the cubes of their semi-major axes. P1 squared over P2 squared equals A1 cubed over A2 cubed, or P squared over A cubed equals constant. For example, imagine an object is traveling around the Sun. What would be the orbital period of the object if its orbit has a semi-major axis of 50 AU? As per Kepler's third law, we know that when we use units of years and AU, if the object's orbit has a semi-major axis of 50 AU, A equals 50, we can cube 50 and then take the square root of the result to get P. P equals the root of A cubed. P equals 353.6 years. Therefore, the orbital period of the object is about 350 years. Now we have come to the end of our lecture, and we have learned what is orbital mechanics or astrodynamics? How has the idea of a satellite been created? What are Newton's laws of motion? What are Kepler's laws? Thank you for your undivided attention.